everybody, in this video we're solving a third order linear recurrence. Our problem says a sub n is 5 times a sub n minus 1 minus 8 times a sub n minus 2 plus 4 times a sub n minus 3, which tells us n has to be greater than or equal to 4 for us to be able to find terms in the sequence. We need to know a few initial conditions. So we're given a sub 1 is 3, a sub 2 is 10, and a sub 3 is 26. Our goal is to find a closed form expression for a sub n that depends only on n, no recursion required. To get started, we're going to form a characteristic polynomial. Instead of a sub n, we're going to write r to the n. Then 5a to the n minus 1 becomes 5r to the n minus 1. Minus 8a sub n minus 2 is minus 8r to the n minus 2, and then plus 4a sub n minus 3 is plus 4r to the n minus 3. We want to make this look a little bit better. Notice everything has a power of r, so we're going to divide by the highest power of r that's common to all pieces of our equation. That happens to be r to the n minus 3. So each term gets divided by r to the n minus 3. Remember, when you divide the same base, you're going to subtract exponents. So now we get r cubed is equal to 5r squared minus 8r plus 4. Let's set the equation equal to 0 and find the roots of the equation. To do that, I'm going to go to Desmos. In Desmos, I graphed f of x as x cubed minus 5x squared plus 8x minus 4. Because this is degree 3, we know we're going to have 3 solutions. I can see I have an intercept at x equals 1, which is a factor of x minus 1. At 2, I see it touches the graph, which means the factor is x minus 2 squared. That's important because we need to use the multiplicity in our solution. Now we can see that r cubed minus 5r squared plus 8r minus 4 is equal to r minus 1 times r minus 2 squared. That has 2 solutions, r is equal to 1 and r is equal to 2, but remember, it has multiplicity of 2. When finding the general solution, each repeated root contributes an extra factor of n. So we'll have a sub n is c1 times 1 to the n, plus c2 times 2 to the n, plus c3 times n times 2 to the n. Because 1 to the n is 1, we can simply rewrite this as c1 plus c2 times 2 to the n plus c3 times n times 2 to the n. We have 3 unknowns, c1, c2, and c3, but we can find them using our 3 initial conditions we had along with the problem. We were given that a1 is 3, a2 is 10, and a3 is 26. We need to plug that into a sub n. So when n is 1, we have c1 plus 2c2 plus 2c3 is 3, which gives us our first equation, c1 plus 2c2 plus 2c3 is 3. Now we plug in n is equal to 2. It gives us c1 plus 2 squared is 4 times c2 plus 2 times 2 squared times c3, which is 10. We can write that as c1 plus 4c2 plus 8c3 is 10. Then, when n is 3, we have c1 plus 2 cubed is 8 times c2 plus 3 times 2 cubed c3 is 26. That simplifies to c1 plus 8 times c2 plus 24 times c3 is 26. Now we have 3 equations with 3 unknowns. We have plenty of ways to solve this, but we're just going to do it using the Desmos matrix calculator. So from the graph I was using earlier, I'm going to hit Tools on the right and just switch to the matrix calculator. We're going to create a new matrix that has 3 rows and 4 columns. That gives us a row for each of our equations and a place to put c1, c2, c3, and the numeric answer. Because I have c1, I enter 1, then I had 2c2, 2c3, and that was equal to 3. Then I again had c1, so I put in a 1. Then I had 4c2, 8c3, and that was equal to 10. Then our last equation, again, was 1c1, 8c2, 24c3, and that's equal to 26. We push return to enter our matrix, and then I hit RREF for reduced row echelon form. Then I enter A, the name of the matrix. This gives us C1 is -2, C2 is 2, and C3 is 0.5, or if you want that as a fraction, we can convert it over. Let's put those values into our equation. We have -2 for C1, 2 for C2, and 1/2 for C3. Let's simplify this a little bit. We'll start by keeping our -2. Then I have 2 times 2 to the n. Since they're the same base, I can add the exponents to get 2 to the n plus 1. Then I have 1/2 times n times 2 to the n. Let's rewrite 1/2 as 2 to the -1. Then I can combine the like bases by adding -1 and n to get n times 2 to the n minus 1. This is our final solution. A sub n is -2 plus 2 to the n plus 1 plus n times 2 to the n minus 1. You can always verify your work by going back to our initial conditions. When n was 1, we knew the value is 3. When n is 2, it should be 10. When it's 3, it's supposed to be 26. So we can plug in our values for n and make sure we get the initial conditions we were given. We can also find other terms in the sequence by plugging in a value like n equals 4 into our new formula. That would give us -2 plus 2 to the 4 plus 1, which is 5. 2 to the 5th gives us 32. Then we would have 4 times 2 to the 4 minus 1. 4 minus 1 is 3. 2 cubed is 8. 8 times 4 is 32. We can add that all together to get 62. You could also check this by going back to our original recursive form, which was 5 times a sub n minus 1 minus 8 times a sub n minus 2 plus 4 times a sub n minus 3. For a4, that would be 5 times a3 minus 8 times a2 plus 4 times a1, which is 5 times 26 minus 8 times 10 plus 4 times 3. This is also 62, which shows us we get the same answer using either the recursive or explicit form.